Welcome. In this video we're going to talk about the production choke. So the production choke is usually located at the Christmas tree. So if we make a line diagram of our wellbore, we have our formation here. Then we have our master valve, wing valves, swap valve, and then we have our choke. Typically we use a symbol like this if it's adjustable, and then we have into assume we have a flow line and we have the separator. Okay, so that's the choke. That's where usually the choke is located. Okay, and the function of the choke we have seen is to bridge pressure. So if I'm going to make a plot of the pressure available from this side of the system versus rate as standard conditions, so we end up that this curve looks something like this. Okay, and then if we make another curve for the pressure required for this part of the system is usually like this. And that means that if I put these two together without any control element, this will be the flow that I'm going to get, the equilibrium flow. But if I want to if I want to produce any value below that number, then, for example, let's say Q1, then this means that this is a pressure I have to bridge. There is a difference in pressure between the available and the required. I have more pressure than what I required, and then this means that I have to apply this choke delta P. So we're going to go in this lecture, we're going to go a bit more in detail into what is inside this box, a magical box that makes this, that has this function to regulate the flow. How does it work? And then a bit about the flow performance of the choke. So here I show a slide that I took from this course. It's a course on wellhead choke design. And I'm not sure if it's accurate, but at least gives you a timeline of how the choke technology were developed and what is being in use, what is used today. And this is related to the development also of the control valve technology that is also used in the process industry. Okay, but you see here, the beginning of the century, you were using a positive choke, also called beam choke, in which you have a change in direction, 90 degrees, and then you have one element which is simply an obstruction, a cylinder of very small internal size, and that's how you created the pressure drop. So this essentially reduces the pressure, increases the velocity, and then it induces some sort of a jet. Okay, and the contraction and the expansion is very abrupt. And if you wanted to, let's say there was depletion, reservoir pressure is going down, this curve is actually going down, and then the delta P of the choke has to be reduced. In that case, I have to bypass production. I have to bypass this choke or close production from the well. I have to open this cap and replace this element by something of a different size. Okay, and if you want to increase production or maintain production, usually something of a bigger size, of a bigger opening. Okay, and we have next generation. You see here, according to this slide, it's before the 1925 needle and seat. Okay, that you have one part which is moving up and down, and it has like a needle shape, and then you have a seat. Looks a bit like this. Again, if it goes down, it's closed, and if it goes up, it's open. And again, the same thing, the fluid changes direction very abruptly and is passing through a very small contraction and then coming out. Then you have the next generation, which you have disc, or also called the Willis type choke, in which I have two discs, and if I put them aligned, then that means very little pressure drop aligned with each other. And if they're misaligned or they are completely misaligned, that they don't coincide, then that means that I have no flow or have very big pressure drop. So one of these discs is stationary, is at the bottom, and then the other one is moving, usually at the top. And then when I rotate this stem, then what I'm doing is I'm rotating the top disc. Okay, here you see one that we have at our department, and here you see I rotate this one, transmit the rotation to the stem, and then this stem rotates this part. This part is moving the top disc, and then I have a bottom disc that is stationary. Okay, then we see here around this 1975, we started having some chokes that are some of the most common nowadays used by the industry. We have the cage type chokes, and this cage essentially have a cage with holes, and then I have something either moving on the inside, in the case of this one, internal plug, or something move on the outside, in the case of the external sleeve, to uh, make the holes to make more holes or less holes open, and then that is how you control the pressure drop. If you have a lot of holes open, that means you have very little pressure drop. If you have less holes available to flow, so that means I have a very high pressure drop. Okay, essentially these external sleeve are the ones that are usually said that they have more resistance to erosion. Okay, so one problem with chokes is that they are working, operating in a very aggressive environment. There is a big pressure drop. That means there is a lot of turbulence, recirculation. You have this also these high velocity jets that can impact the walls and they can cause erosion, loss of material over time. And you have flashing, vaporization of gas coming out very quickly out of the oil. So this can cause it's a very aggressive environment, and this can affect negatively the life of the choke. So that's part of the thing. What induced the movement in evolution of the technology of the choke. So if you see here some of the problems you see in this choke, this pin choke, we are looking at this flange here from this side, and you see that this jet might be hitting some of the walls, and then it might cause some erosion, like it is shown here. This is where I took it from. Okay, I don't have any images of what occurs on a needle and seat choke, but what occurs is that this loses material, essentially becomes like curved, doesn't become conus anymore, and then with time it's going to break, and then it will stop working. Here is one interesting that I found on this dual disc choke. You see here the erosion. This is upside down, sorry for that, but this is where the discs are. This is the exit disc, and then this is all the way to the bottom. So this is upside down. This will be corresponding to this part, and this one will be corresponding to this part. And you see that you have erosion, some erosion here, but you have a lot of erosion there. Okay, and you also have erosion in on the discs themselves. You see here that you have like some patterns at some side it has more erosion than others. Yeah, and you see here on that paper also you have a simulation that tells you why that's occurring, and you see when the choke is very closed, then the jets are essentially shooting on the walls where they're very close. That's why you get this erosion, and also why you get this erosion here. But then when it's almost fully open, then these jets are hitting the wall, this wall that are here. So even when they are in the fully open position, they're producing some jets that are actually causing erosion. So one advantage regarding erosion with cage plugs is that they are symmetric. Usually they make them symmetric. So the hole has also one hole on the opposite side. Yeah, and that is to avoid the jets to be hitting the wall or the surface, so they hit each other, and then with that they make the energy dissipation, and you avoid points where you might have erosion in the material. And that's why they are a bit more resistant to erosion. But of course, that doesn't mean that they are completely resistant. Here you see an image where you have the cage and the plug, and actually you have a lot of erosion, and this was caused by sand. Okay, if you have not only the high velocity and the fluid, but also if you have solids, they help really to take out the material out of the wall because they hit the wall and then they remove the material. So this choke also have a bit of a fundamental different how to operate. So this essentially is adjustable, is not adjustable. Like this one I have to replace every time, so it's a manual adjusted. And all of these I can adjust by rotating or using an actuator to change the position. Okay, but essentially they have a different, slightly different behavior. So here I have plotted is doing some experiments in which the choke is subject to. Okay, let's use a symbol of a choke. 1 and 2, and they are subject to the same delta P. So P1 is constant, delta P is constant, and also the fluid, the type of fluid I have is constant. Okay, so in this case, let's say water. Okay, so that means that if I change and open the choke from 0 to 100, I call it here choke opening. Some people also say how much the stem has traveled up. Okay, because many chokes simply when the stem travels up, I have is fully open. When the stem travels down, it's fully closed, and also for all the others. Okay, so essentially it tells you, and this is the rate divided by the Q rate max that I'm able to achieve. That will be, if we're fully open, that will be the maximum, and then I divide all the rates by the maximum, okay, just to normalize, just to make it in terms of one. Okay, and you see here that you have different behaviors. So when I'm opening the choke, I might follow this trajectory, or this trajectory, or this trajectory. And essentially, this gives you some advantages. For example, here, if you start opening this quick opening, you start opening, you see that you have very big jumps in rate. Okay, while for the equal percentage, the increasing rate will be very gradual. Okay, so if you are operating in you need to operate the choke almost close, and you need to have very good control. Probably this equal percentage is a better choice than the quick opening, because the quick opening you make big jumps in rate when you move the stem. Okay, well, the equal percentage is very small jumps. Okay, if you are in the region in which you are almost fully open and you need very good control, maybe the quick opening is a better choice, because here big changes in opening are going to give you small changes in rate, but the equal percentage is the opposite. Okay, so everything depends on what you need, and linear is something in between. Okay, so typically quick opening, these are needle and sit. They are sometimes also linear. The linear is the dual disc, and these are the cage type chokes. Okay, so just be careful that they also operate when you open them and close them. They also operate in a slightly different manner. And we have to be careful depending on the accuracy and where we want that. For example, if we have a small choke that is operating on that range and is an equal percentage, well, we might want to maybe use a bigger choke where we are going to be operating in that region. Okay, and then it will allow us to have better control. Regarding actuation, you see here this choke we have in our department, the figure I showed before. It has a wheel, it's manually actuated, for example, and in this case it simply continues. Here you have at the top, if you see from the top, you have a needle indicating where you are, and here it says bean size 64th of an inch. Okay, so just the equivalent to a bean choke, to a positive choke, the one we showed up here. Okay, and it tells you different 8, so 0, fully closed. Here is the range where it's going to be very choked. Okay, 32 of an inch, 40, 48. Then it's open to 1 inch, and here you have is more than an inch. Okay, so this is a continuous actuation, but typically when I have, for example, subsea chokes that I cannot have manually or personally access to the choke, then typically they are hydraulically actuated. And many times they're not continuous, simply don't rotate and I get anything in between, but they are discrete. Okay, so you see here you have one hydraulic piston, for example, is pushing down, and every time it pushes down, simply it rotates this one tick by one tick, and here you have 1, 2, 3, 5 ticks, and then every tick you give essentially advances the choke to one position. So there are discrete steps and discrete actuation, and in that case it's easier. Why I do that? Because it's easier to count how many, let's say you know that you need 100 steps to reach from fully open to fully closed, and if you're at 50 steps, then that means that you're halfway. Okay, so it's easy to control just counting the number of steps you have, rather than using this continuous, that if you don't have access to this indicator with camera, for example, and you don't have a system in which you have some magnetic position system, then it's not very convenient. Now we're going to go into more details of what is the flow performance of the choke, what is happening inside the choke. So all chokes, even though they might be more complex than others, so some might be more complex than others, All of the chokes, usually what they are represented or what we can visualize them has a sudden contraction. You have a channel, sudden contraction, and then a sudden expansion. Okay, here, for example, I have just one flow path. Here, the construction is made in a different way, but it's essentially the same thing. You have a sudden contraction and expansion. Here you have, instead of having one flow path, you have two flow paths. So you can go through two flow paths and you assume they're kind of identical, but essentially you have again the same thing, sudden contraction and sudden expansion. And here you have, well, many flow paths depending how many holes you have in the cage, but essentially you also try to say that all of them behave the same way and you have a sudden contraction and sudden expansion. So all of these chokes, like I can visualize them as if they were essentially just like a bean choke. In which the flow has a very abrupt acceleration, a very abrupt increase in velocity, and then it expands. This section of the choke is what we call the throat of the choke, in which I have high velocity and very low pressure. Okay, so if we were going to plot the streamlines of the fluid going inside, this is how they might look like. And let's now try to plot the pressure because we are concerned about rate. These are two things that we want to know about the choke, is mass flow and is also the pressure. Okay, so let's look at the pressure along the choke. And typically here we have, this is the inlet pressure. And when it's reaching this sudden contraction, it suddenly drops very much. And then you have a recovery of pressure in the throat. Okay, so this is P in. And then here at the sudden expansion, typically that's why I do it sudden, such that there is not much pressure recovery. So I might have an increase, but then the pressure hopefully doesn't increase much. Okay, so this is my P out, and this is the delta P that the choke has to provide. If the geometry was a bit smoother, so you have, for example, this jump that goes below this pressure, this is typically caused by this sudden contraction. Okay, if you had a more smoother profile, something that is used, for example, for metering, okay, then I will have, hopefully I will have, because I want to use it for metering, not for reduction of pressure, so then you will have a smooth reduction of pressure and then an increase in pressure. Okay, so this you don't have this big jump, but probably you will have if this were smooth, so then you have a kind of a very smooth transition from here to here. So we are going to do to try to understand what happens on a choke. We are going to be using this clip from a video from this National Committee for Fluid Mechanics film. This was an initiative led by Professor Asher Shapiro, teaching mechanical engineering at MIT, where they gather a lot of experts in different universities in the US and they recorded films about different topics. Again, the one we are going to be using is called Channel Flow of Compressible Fluid. And you see here in this website, there are all the videos and there are notes to these videos and it's very interesting, so I recommend you to take a look. Okay, but essentially they run experiments in a channel that has this geometry. Okay, that you see that it's not a sudden contraction like a choke, but still we can use this video for our choke purposes. These are typically used for aerodynamics, for example, for rockets, for things that are going to fly, for planes, propulsion engines. Okay, we are not using it for that. We're using it for a different purpose, but it's the same principle. Okay, so you see that it's smooth, a smooth contraction, and then also a smooth expansion. So what they did, they had this channel, and this I think is symmetry. They actually this channel should be symmetrical, but they use half just to because it's the same if you use only half or if you use all the complete channel. Okay, so I'm going to make a sketch. Repeating simply the sketch of how the channel looks like. And then here at the end, they put a valve. And they had together with a vacuum pump or a compressor. And finally, this is discharging to the atmosphere. Okay, and this is also taking from the atmosphere. So this means that this is at a constant pressure, at a constant temperature, and also, of course, air, so constant properties. Okay, so essentially it's air, and by using this, all of this system, this valve and this vacuum pump, essentially what they are doing is that they are controlling the pressure that I have here, P2. So P1 is constant and P2 is they can lower it down below atmospheric. Okay, so P2 is below, typically equal, less or equal than P atmospheric by using this arrangement of valves. Okay, but that's how it was done. And this one is a vacuum pump. Okay. So we will see what happens, and essentially they had a very interesting. They had the visualization of the channel. See how it looks like at the top. And then at the bottom, they connected two different holes at the bottom of the channel. They connected hoses, and these hoses, they had a column of mercury. So they're able also to visualize the pressure. So each one of these black columns that you see there is essentially the pressure level. So initially you have some pressure at the inlet of the channel, and then as you go along the channel is going down if you have flow. Okay, you go reach the minimum pressure at the throat and maximum speed, and then it starts to increase. When the channel is expanding, the pressure is starting to go up again, and then you reach the outlet pressure. And of course, to induce flow, you should have a difference between the inlet pressure and the outlet pressure. But essentially, that's what the bars are indicating. Okay, so we're going to see a video of, and the sequence is going to be, initially that pressure is going to be a bit low, below atmospheric, and then it's going to be reduced and reduced and reduced. So it's going to help us to see what happens with the choke. Essentially, that experiment is delta P and see what happens with the mass flow rate. Okay, in this case, P1 is kept constant in this experiment, and then P2 is being reduced. It's not constant, it's varying. Okay, so you want to see what occurs. And you know, of course, if the two pressures are the same, because it's a horizontal channel, so simply in the points 0 and 0. Okay, but then as I reduce the pressure too, that means that I increase the pressure drop. The pressure drop is defined as delta P is P1 minus P2. Okay, as I increase, that means that I'm reducing this guy further and further, so what occurs with the rate? And intuitively, what we should expect is, well, if I put more pressure drop, okay, so if I reduce this pressure more and more, I will be able to pull more rate. Okay, so you see that from intuition, you might say, well, this relationship is like non-linear. Is doing something like that. And essentially, you will see that that's the case, but something strange happens someplace in between. So it doesn't continue like that forever, but something happens in between. Okay, so we're going to see the video, and then we discuss what we observe. Okay, so you see here you already have some established flow through the channel. You have some pressure, and this pressure is slightly lower. And then you have this pressure distribution. Here you have the throat. He's going to indicate where the throat is. And then what they are going to do is they're going to reduce that pressure further, the outlet pressure. And you see what happens is that this is the pressure that is being reduced, and you see that the pressure of the throat actually goes down. So that means that the velocity is increasing. So here the mass flow is getting higher and higher and higher. Okay, but take a look here, the noise. There is going to be a change in the noise.
The noise level suddenly changes.
When you reach this pressure goes below some limit. Okay, and then look at what happens with the pressure. I reach now a point that is called the critical conditions at the choke. If you see, if I continue reducing the pressure further, here you see it's going down, well, this curve doesn't change anymore, this part of the curve. The only thing that is changing is the part downstream this point. Okay, so you see that pressure is changing getting lower and lower and lower. And now the point of minimum pressure is not anymore here, but essentially is moving further down the geometry, which is very strange. Okay, it doesn't correspond anymore to the point where I have the minimum area. That point is where essentially the pressure distribution remains constant upstream that point, but downstream that point, essentially the pressure can continue going down and down and down. And you see, as before, I had like a very more or less like a smooth distribution or image distribution, but here I have a smooth distribution all the way up to here, and then here I have a sudden jump. I have a sudden change in pressure. Okay, that this jump that I have here. So that's the clip. And this is the pressure distribution. This is what we call the subcritical regime. This one, in which I reach these conditions, is a critical. Okay, and here I have the supercritical. Can you see how the three, actually they kept the three distributions, but the critical, subcritical, critical, and supercritical. Okay, where you have this jump in, so what happens with the essentially what occurs is that after you reach the critical at this delta p, let's say you reach the critical, this is the delta p critical, then simply it doesn't change the mass flow. Simply I'm going to have the same mass flow because you could relate somehow the mass flow to this shape that you have at the entrance. Okay, and if that shape actually remains constant, it doesn't change anymore. What is going to change is after that. Then that means that the mass flow is essentially constant. Okay, so that tells you that this behavior is something like this. Okay, from that point, simply going to remain constant. Okay, until of course here I reach some time that the P2, I reach a limit. Okay, where P2 is equal to zero. Okay, 0 bar or zero pressure. So why does this occur, and what does it mean really to have critical pressure? Well, critical, if I make perturbations of pressure in this system, so let's say that here I were changing the pressure, right, and that the change in this pressure is propagated to the inlet. That's how the fluid is kind of knows that it has to increase the mass flow, because now this pressure is going down, and now it knows, well, I should start flowing more flow. Okay, so it's like the changes in pressure, they propagate at a certain speed. They're called the speed of sound, or speed of the pressure propagations in the medium. Okay, and they reach this point. When I have the critical, exactly at the critical point, that means that the velocity at the throat, the velocity at this point where I have the minimum area, is equal to the velocity of the sound. Okay, sometimes you see velocity of the sound referred to as A in the air, velocity of sound in in the air. Okay, and this typically in the air is like 300 meters per second. Okay, but in the fluid, it will depend what kind of fluid you have here. Okay, in the choke, it will depend on what kind of fluid. So when I reach that velocity, that means that any pressure perturbation that I change here, if I reduce this pressure further by using this arrangement of valve and vacuum pump, it doesn't know, the inlet doesn't know that that pressure has changed, because simply at this point, it cannot reach, it's propagating up, 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 but then it cannot reach further than that. That's where it's going to stop. Okay, and if I continue reducing the pressure at the outlet, so then it's going to affect just the downstream of that point, just where I have the downstream. Okay, so and this is something a bit more complicated. So here the fluid is supercritical. That means it's traveling at velocities higher than the speed of sound. Okay, and suddenly you have a shock wave in which it's going to change to subcritical. Okay, so this is supercritical conditions, and then that also occurs in a choke, but we're not going to discuss too much about it. For us, what we are more concerned is this chart, okay, how it behaves. If we're going to extrapolate to what occurs on a choke, let's say that this choke is operating with dry gas, we can say that the delta P across the choke, that means essentially reducing the pressure at Q of gas, okay, then it's going to be something like this. And this is, and at here it reaches at some point. Okay, so this condition occurs when essentially the ratio between P2 divided by P1 for gas is typically something between 0.5. Okay, it's half, or 0.6 or zero point 0.4, it might be a bit different, but it's usually 0.5. And sometimes you can use that as a rule of thumb for other, when you have multi-phase. Okay, but this is if you're operating usually for gas, is more applicable. Okay, that means that the delta P, here we're referring to delta P, is going to be equal to P1 minus P2. And then we can say this is P1, 1 minus 0.5, right? P2, according to this equation, is equal to P1 times 0.5. Okay, and then I can take the P1 as a common factor. Okay, so this the delta P critical is equal to P1 times 0.5. Okay, that's where my critical pressure is. So now I want to ask you what happens if we make the choke smaller. Let's say now that we have our throat, and let's say we change the size of the choke, and now we can make it smaller. We have all the same conditions, inlet pressure is the same, inlet pressure is the same, uh, but the only thing is that the choke, the geometry of the choke is now different. Well, if the choke, so this, let's call it the choke opening, or if we, a smaller choke, or if we use a different opening of the choke. So this will be choke opening, 80%, let's say, and now we have to simply close it, and then we're using 60%. Okay, and so intuitively in these regions, you might say, well, it takes simply the same delta P, simply drawing less rate. Okay, so the curve here, this curve at the lower part, is essentially going like this, also from 0, but now the same delta P, because the choke is 60% closed, okay, is going to take less rate. But what occurs with the point of the critical conditions? Well, you see that the critical conditions they are achieved, they are only dependent on the inlet pressure. They're not dependent on anything else. Okay, so you actually, I'm going to, if the inlet pressure is constant, is the same, I'm going to reach critical point conditions at the same point. Okay, so that will mean that this is going to be the behavior for a choke opening equal to 60%. Okay, CO in this case, choke opening. Okay, so when I start to reduce the opening of the choke and the inlet pressure is constant, that's the effect I have. My critical rate is going to be less and less.